Okay, in this lecture we're going to cover our section 6.3 material on orthogonal projections. Now in our last section we had considered the orthogonal projection of a point in R2, so maybe thinking of it as the terminal point of some vector in R2, onto a line passing through the origin. And in this section we're going to extend that concept to an analog in Rn, that is in dimensional space. So let's say that we're given a vector y in some subspace W of Rn. Then there is some vector y hat in W such that y hat is the unique vector in W for which the difference y minus y hat is orthogonal to W, and y hat is the unique vector in W which is closest to y. So to visualize this, let's consider some subspace. Let's call this subspace W of Rn. And suppose that we have some vector. So let's say we have a vector y. And maybe I can think about its representation as having its initial point at the origin for in-dimensional space, which we know has to lie in W since W is a subspace. So there is some vector which is called y hat in W, which is the unique vector which is closest to the vector y. So we can think about dropping a perpendicular from the terminal point of y onto the terminal point of y hat so that this distance is a minimum. And the vector which is the difference of these, so that is the vector which we might call z, or y minus y hat, is the unique vector such, or y hat is the unique vector such that this difference is orthogonal to y hat. And we can see that that same vector would be shown here. Okay. So what we're going to consider in this section is the extension of an orthogonal projection of a vector onto a line in R2 to the orthogonal projection of a vector in n-dimensional space onto some subspace of Rn, which we're calling W. And this projection is unique and defines the closest vector in W to the vector y. So let's consider the following in order to arrive at this result that we're going to consider. Let's note that whenever a vector y can be written as a linear combination of vectors u1 through un, which are vectors in Rn, the terms in the sum for y can be grouped into two parts, so that our vector y can be written as the sum of two vectors z1 and z2, where z1 is a linear combination of some of the basis vectors ui, and z2 is a linear combination of the rest of the basis vectors ui. And it turns out that this concept is especially useful if the set of vectors u1 through un is an orthogonal basis. So recall if we can write y as a linear combination of vectors u1 through un, that means that y can be written as some linear combination of these vectors. So if I group certain terms together, say maybe my first two terms, I could think about the linear combination of the vectors u1 and u2 as being some vector z2, and then all of the remaining terms I could think of as some vector z2. And in the event that we have an orthogonal basis, it turns out that we can decompose y into a sum of two vectors, one which lies in a subspace W and one which is orthogonal to that space. Let's consider the following problem. Suppose that we have a set of vectors u1 through u5, which is some orthogonal basis for R5, and let y be the linear or some linear combination of those vectors, u1 through u5. And then let us consider the subspace W, which is spanned by the first two basis vectors, u1 and u2. And we're supposed to then write y as the sum of a vector z1, which lies in W, and a vector z2, which lies in the orthogonal complement of W. So let's see how this would work. If we have our vector y written as the linear combination c1 u1 plus c2 u2 plus c3 u3 plus c4 u4 and plus c5 u5, then if I were to group the first two terms together, I have a linear combination of the vectors u1 and u2. So let me call this vector z1. And clearly, since z1 is a linear combination of the vectors u1 and u2, it lies in the space W, which is the spanning set of u1 and u2. Now, if I group my remaining terms, the linear combination of these vectors u3 through u5, let's call this vector z2. And we need to show that this vector lies in the orthogonal complement of W. So that becomes our question. Is this vector in the orthogonal complement? So to show that Z2 lies in the orthogonal complement of W, it's sufficient to show that Z2 is orthogonal to the vectors which form the basis for W. So here, let's say to show that our vector Z2 lies in the orthogonal complement of W, it is sufficient to show that Z2 is orthogonal to the vectors or to the basis, which consisted of u1 and u2 for our spanning set W. Recall that result from section 6.1. In order to show that a vector is in the orthogonal complement of a space, we only need to show that it is orthogonal to the basis vectors for that space. So let's consider the dot product of Z2 with U1, the first basis vector. So Z2 is defined as C3 U3 plus C4 U4 plus C5 U5, and we're taking the dot product with U1. So using the distributive property of the dot product, this is the same as C3 times the dot product of U3 with U1 plus C4 times the dot product of U4 with U1 plus C5 times the dot product of U5 with U1. But now in our problem statement, we were told that this basis of U1 through U5 is an orthogonal basis. So all of these basis vectors, u1, u2, u3, and through u5, are mutually orthogonal. So the dot product of any two distinct vectors is 0, so we have a value of 0 here. So since the dot product of z2 and u1 is 0, that means that they are orthogonal. And similarly, if we consider the dot product of z2 with u2, since u2 is orthogonal to u3, u4, and u5, we would again have a 0 value for this dot product. And so our vector z2 lies in the orthogonal complement of W. So in this example, we've illustrated if we have an orthogonal basis for our space, R5, then we can decompose any vector within that space into the sum of two vectors, one lying in a subspace W and the other being orthogonal to that subspace. Now, our next theorem will show that this decomposition that we're considering can be computed without having an orthogonal basis for all of Rn. In fact, it is enough to have just an orthogonal basis for the subspace W. So this result, theorem 6.8 from your text, is known as the orthogonal decomposition theorem, which says if we have a subspace W of Rn, then for each vector y in Rn, we can write that vector uniquely in the form y is y hat plus z, where y hat is in the subspace W and z is in the orthogonal complement to W. And in fact, if the basis for our subspace is an orthogonal basis consisting of vectors u1 through up, then the vector y hat, which lies in W, can or has weights given by the dot product of y with the respective basis vectors u1 through up divided by the dot product of those basis vectors with themselves. And the vector z, which lies in the orthogonal complement, would then just be y minus y hat. So this vector y hat, which we're talking about, is referred to the orthogonal projection of y onto the subspace W, and it's written as follows: the projection of y onto the subspace W. So let's look at an example of this. Here we're told to consider the three vectors u1, u2, and y, which are vectors in R3. And we're supposed to first verify that the set u1, u2 is an orthogonal set, and then find the orthogonal projection of y onto the subspace W, which is spanned by u1 and u2. So that would be a plane in R3. So the first part of this problem, we need to verify that u1 and u2 is an orthogonal set. So since our set consists of only two vectors, we just need to ensure that they are orthogonal. So since the dot product of u1 and u2 is equal to 0 minus 1 plus 1, which is 0, that means that the set consisting of these two vectors, u1 and u2, is an orthogonal set. Now, in order to find the orthogonal projection of y onto W, we're going to make use of the orthogonal decomposition theorem. So here we need to compute the dot product of our vector y with each of the orthogonal basis vectors, as well as the dot product of these basis vectors with themselves. So here we will compute the dot product of y with u1, which would be equal to, let's see, negative 24 minus 4, so negative 28, and then plus 1. So we have negative 27. Taking the dot product of y with u2, we have 0 plus 4 plus 1, which gives us 5. And then taking the dot product of u1 with itself, we have 16 plus 1 plus 1, so 18. And the dot product of u2 with itself is 0 plus 1 plus 1, so 2. So, using our theorem, the orthogonal projection of this vector y onto the subspace W spanned by u1 and u2 is the vector, well, we can use both notations here. So we could denote it as the projection of y onto W, or equivalently y hat. So our first component, or our first weight, is the quotient of the dot product of y with u1 divided by the dot product of u1 with itself. So we would have negative 27 over 18, or negative 3 halves of our basis vector u1. Plus, for our second weight, we would have the quotient of the dot product of y with u2 divided by the dot product of u2 with itself. So that would be 5 halves of u2. Now we know what u1 and u2 are equal to. So here we have negative 3 halves of u1, which was negative 4, negative 1, 1. And then plus 5 halves of u2, which was 0, 1, 1. So for our first component, we have a positive 12 halves, or 6. Our second component, we have 3 halves plus 5 halves, so that is 8 halves, or 4. And then for our third component, we have negative 3 halves plus 5 halves, which is 2 halves, or 1. So this would be the orthogonal projection of y onto the indicated subspace. So let's look at a similar one. So here we are considering the set of vectors u1, u2, and y, again vectors in R3, and we're supposed to verify that the set u1, u2 is an orthogonal set, and then find the orthogonal projection of y onto the subspace W spanned by u1 and u2, so again that would be a plane in space. And then write y as the sum of a vector in W and a vector which is orthogonal to W. Okay. So again, first we need to verify that this is an orthogonal set. So since it consists of only 2 vectors, we only need to consider the dot product of those 2 vectors, u1 and u2, which would be, let's see, negative 1 plus 3 minus 2, which is indeed 0. So the set consisting of the vectors u1 and u2 is an orthogonal set. All right. Now we're supposed to find the orthogonal projection of y onto W. So as we did in our previous example, to make use of our orthogonal decomposition theorem, we must compute the dot product of y with u1, which would be, let's see, negative 1 plus 4 is 3 plus 3 gives us 6. The dot product of y with u2 is equal to 1 plus 12 minus 6. So that leaves us with a value of 7. And then the dot product of u1 with itself would be 1 plus 1 plus 1, or 3, and the dot product of u2 with itself is equal to 1 plus 9 plus 4, so 14. So finding the orthogonal projection of the vector y onto the subspace W, which can also be denoted as y hat, we would have for our first weight the quotient of the dot product of y with u1 over the dot product of u1 with itself, so 6 over 3, or 2, times u1, plus for our second weight we would have the quotient of the dot product of y with u2 over the dot product of u2 with itself, so 7 over 14, or 1/2 of u2. So let's find this vector. This would be 2 times u1, which was 1, 1, 1, plus 1/2 of u2, which was -1, 3, -2. So for our first component, we have 2 minus 1/2, which would be 3/2. Then we have 2 plus 3/2, which is 7/2. And then our third component is 2 minus 1, so 1. So we found the orthogonal projection of y onto W, and the last part of this problem is to write y as the sum of a vector in W, so that would be this orthogonal projection, and a vector orthogonal to W. So to get that orthogonal vector, which we're calling z, we would take y minus this orthogonal projection, y hat. So here y was the vector -1, 4, 3, and then we are subtracting the orthogonal projection, which we found to be 3/2, 7/2, and 1. So this leaves us with the vector -5/2. 4 minus 7/2 would be 1/2, and 3 minus 1 is 2. Now, when we're working through these problems, one way that we can sort of check our work throughout, so our previous theorem states that this vector z should be orthogonal to the subspace W, which is spanned by u1 and u2. So we can check that this vector z is orthogonal to both u1 and u2 by taking the dot product to make sure that our work is correct. So as a quick check to make sure that we're correct, we can see that the dot product of z with u1 and the dot product of z with u2 is equal to 0, so that z does indeed lie in the orthogonal complement of W. And so the decomposition that we're after for this vector y is the sum of y hat and z. So we found y hat to be 3/2, 7/2, 1. And then we're adding the vector z, which was -5/2, 1/2, and 2. And we can see that if we sum these two vectors, we do indeed get the vector y. Now, in the next part of this section, we'll talk about some properties of orthogonal projections. So let's start by saying the following. If we have a basis of vectors u1 through up, which is an orthogonal basis for a subspace W, and y is in W, which would be the span of this set of vectors, then the orthogonal projection of y onto W would just be y itself. So that is the orthogonal projection of a vector within a subspace onto that subspace is just the vector itself. Now this fact also follows from our next theorem. So theorem 6.9 is called the best approximation theorem, which says the following. If W is a subspace of Rn and y is some vector in Rn, then if we take y hat to be the orthogonal projection of y onto W, then y hat is the closest point in W to the vector y, in the sense that the distance from y to y hat, that is the length of the vector y minus y hat, is less than the distance from y to any other vector, v, which lies in W, which are distinct from y hat itself. So this vector y hat is called the best approximation to y by elements of W. So let's consider a problem in finding this best approximation. So if we consider the vectors v1, v2, and z, which are vectors in R4, we are asked to find the best approximation to the vector z by vectors of the form c1, v1 plus c2, v2. So that means vectors in some subspace W, which would be spanned by the vectors v1 and v2, since we're looking at vectors that can be considered as a linear combination of those two vectors. In order to use our previous theorem and find this orthogonal projection, we need to make sure that v1 and v2 are an orthogonal set. So if we were to consider their dot product, v1 and v2, we have 10 plus 0 minus 4 minus 6, which is indeed 0. So that means that the set consisting of vectors v1, v2 is an orthogonal set which spans W, so it is an orthogonal basis for our set W. So to get our best approximation of the vector z by elements of the subspace W, we need the orthogonal projection of z onto W. So using the same approach, or using our same theorem, theorem 6.8, we would need to compute the dot product of z with each of our basis vectors, v1 and v2. Now the dot product of z with v1, let's see, we have 4 plus 0 plus 0 plus 3, so 4 plus 3 is 7, and then the dot product of z with v2 would be 10 minus 8, so that's 2 plus 0, and then minus 2 gives us 0. And then the dot product of v1 with itself would be 4 plus 0 plus 1 plus 9, so altogether 14. And then the dot product of v2 with itself would be equal to 25 plus 4 plus 16 plus 4, which gives us 49. So the orthogonal projection of our vector z onto the subspace W spanned by v1 and v2 is given by the ratio, so our first weight is the ratio of the dot product of z with v1 divided by the dot product of v1 with itself, so that is 7 over 14, or 1/2 of v1, plus our second weight would be the ratio of the dot product of z with v2 over the dot product of v2 with itself, so 0 over 49, which is 0 v2. So we have just half of v1, which would give us the vector 1, 0, negative 1/2, negative 3/2. And this is our best approximation of y by elements of W. It is that orthogonal projection. Okay. So let's consider another problem. Suppose that we have the vectors v1, v2, and y, which are all vectors in R4, and we're asked to find the closest point to y in the subspace W, which is spanned by v1 and v2. We can verify here that v1 and v2 form an orthogonal set if we consider their dot product. So let's say since the dot product of v1 and v2 is equal to, let's see, -4 minus 2 plus 0 plus 6, which is indeed 0. Then we know our set of vectors v1 and v2 is an orthogonal set. And since v1 and v2 span the subspace W, this is an orthogonal basis for the subspace W. So in order to find the closest point to y, well, the closest point would be the orthogonal projection of y onto the subspace W. So as with our previous examples, we need to compute the dot product of y with v1. So here we would have, let's see, 3 plus 2 minus 1 plus 26. So that leaves us with, let's see, 5 minus 1 is 4. And then plus our 26 would be 30. Now the dot product of y with v2 is -12 minus 1, so -13 plus 0 plus 39. So 39 minus 13 leaves us with 26. Then the dot product of v1 with itself would be 1 plus 4 plus 1 plus 4. So that gives us 10. And the dot product of v2 with itself is 16 plus 1 plus 0 plus 9, which is 26. So the closest point to the vector y in the subspace W is given by the orthogonal projection of y onto W. So again, using our orthogonal decomposition theorem, we would have our first weight as the ratio of the dot product of y with v1 over the dot product of v1 with itself. So 30 over 10 gives us 3 for the weight of v1. And our second weight would be the ratio 26 over 26, which is 1, times v2. So let's see what we have. Our first vector, we're taking 3 times that vector, so we would have 3, -6, -3, 6. And then we are adding the vector v2, which was -4, 1, 0, 3. So summing these vectors, we have -1, -5, -3, and 9. So this would be a vector in W, which represents a point in 4 space, which is closest to the point y in R4. Now in part B, we're asked to find the distance from the vector y to the subspace W, spanned by v1 and v2. So if we know the closest point to y in the subspace W, the distance would be given by the distance between those two vectors. Let's say the following. by the best approximation theorem, the distance from the vector y to the space W, which is the subspace of R4 spanned by the vectors v1 and v2, is given by the distance between those vectors, y, and the orthogonal projection of y onto W. So that vector is what we've been denoting as z. So let's compute that vector. Z, which is found by taking y minus y hat. Well, y was the vector 3, -1, 1, 13. And then we are subtracting the vector y hat, which we just found to be -1, -5, -3, and 9. So taking this difference, we have 4, 4, 4, and 4. So our distance that we're interested in is the length of this vector z, which is the square root of the sum of the squares of its components. So 4 squared for each term gives us a 16. So we're left with the square root of 64, which is 8. Now, the last theorem in this section really just illustrates how our formula for the orthogonal projection of y onto a subspace is simplified if our basis happens to be orthonormal. So theorem 6.10 says in the event that the vectors u1 through up are an orthonormal basis for the subspace W of Rn, so that is, they are an orthogonal basis and each vector is a unit vector, length 1, then the orthogonal projection of y onto W is the linear combination of u1 through up, where the weights are now just given by the dot products of y with these basis vectors. Now, why would that be true? Well, in general, if we're looking at our weights that we've been using, we would have something of this form. But if each of our vectors is a unit vector, then this dot product of that vector with itself must be equal to 1. So we're just left with the numerator in that case, the dot product of y with these unit vectors. And another way to express this is if we're considering the matrix U, which would have these orthonormal basis vectors as its columns, then the orthogonal projection of y onto W could be written as the product of U with U transpose times y for any vector y in Rn.